Hello, I'm Michelle Doherty. I'm head of department, and it is so nice to see everybody here in person. I know we have people online as well, but just being able to do this and see people's faces as we do it is really great. So I'm so pleased to have you here with us to celebrate Stuart's promotion to professor, which happened back in 2021. And this celebration has been a long time in coming due to COVID delays. So, a bit of history for Stuart. I'm going to behave. I'm not going to tell any stories about you. I've asked Zolf to come up with some stories for later. So Stuart studied for his MSci degree here at Imperial College and chose to stay with us, and he got his PhD degree here in 2005. And we were then very fortunate when he decided to start his academic career here, and he joined the plasma physics group in August 2005, so just after he had finished his PhD. He was then awarded a Royal Society University Research Fellowship from 2007 to 2015, and then a little bit of time after that he was promoted to Professor of Laser Plasma Physics, as I said, in 2021. Now, he's an outstanding experimental physicist. We're really proud of all that he does and the work and the research that he does in the department. And he's renowned for his pioneering work developing compact particle accelerators using high-power lasers and plasmas, and he's going to talk to you about some of that work today. He's also pioneered the use of laser wake field accelerators as a platform for studying strong field QED physics. But on top of the research that he does, he was instrumental in setting up the Institute of Physics Malcolm Haynes Prize in Plasma Physics, and this was specifically earmarked for early career researchers. And he was also a founding member of the Fellows Forum at Imperial, which provides support to independent research fellows. On the teaching side, he was awarded the Faculty of Natural Sciences Award for Excellence in Teaching in 2010, and he's a passionate science communicator. As you're going to see this evening, no pressure at all. And he galvanizes his students with his love of physics. But before I give the floor to him, a little bit of housekeeping. If a fire alarm goes off, it's not planned, so it means it's real. And if you can follow people from the department who will take you to where it is that we will need to stand to be able to get out of the building. Stuart's got two different demonstrations in today's talk. They might be a bit noisy, and there's some flashing lights as well, so just to give you a warning, I think you've got some slides that give us a warning that they're about to actually happen. For those of you who are online, you are able to submit questions at any time, and on your screen on the side there should be a Q&A section where you can do that. Just to let you know, the event is being recorded, and so if you don't wish your name to be read out, those of you online, you can submit the question anonymously. So, with that, it gives me great pleasure to hand over to Professor Stuart Mangles to tell us about recreating stars and quasars with lasers and plasma accelerators. Stuart.
Thank you very much, Michelle. That's not put me under any pressure at all. So I'm going to talk to you about some of the research I've been doing over the last, I don't know, some years, too many years that I want to remember, in particular about how we're using laser plasma experiments to try and recreate the sort of conditions that you get in quasars and other stars and things like that. So I'm going to keep going. So without further, what was I going to say? The nerves have kicked in. Basically, the Earth is pretty boring, okay? So this is a very beautiful picture, but the pressure of the air around us is measured in 1 bar. The temperature is only about 20 degrees. Compared to the rest of the universe, or many places in the universe, that's really quite dull. So if I go to a gas giant planet in this solar system, it's Jupiter, you might not recognize it, it's taken from the pole. Inside there, you get pressures of not 1 bar, but 100 million bar, and not temperatures of 20 degrees C, but 24,000 degrees C. And that's just a planet. If you go inside a star, this is our sun taken in UV, then the temperature can reach 15 million degrees, and the pressures inside there are 265 billion bar. Okay, so really, really extreme stuff. So in terms of these extreme temperatures and densities, so there are some really kind of key questions that we're trying to answer, or ask and then answer, and which is how does that matter actually behave inside these extreme conditions? So for example, it's really hard to know how matter behaves in quite dense but cool stars called red dwarfs, and it's quite hard to understand how it works on the surface of white dwarfs and also inside these giant planets. I'm going to talk more about that in a bit. But it's not only about, there's actually two threads to my talk. I'm going to flip between them all the way through, so I'll try and keep reminding you. So it's not just about extreme temperatures and pressures. I'm also going to talk about electromagnetic fields. So in the universe, it tend to be magnetic fields. So the magnetic fields on Earth, they're only about 30 microtesla, the ones generated by the Earth. Even so, they lead to the beautiful phenomena like the aurora. If you go to the sun, if you've ever looked at a picture of the sun, you see all these prominences. That's plasma following the magnetic field lines. And there, it's a huge field compared to the Earth. It's 0.1 Tesla. This is a picture of a quasar. I think this is the first quasar discovered. It's about 2.5 billion years away if you travel at the speed of light. The fields around that sort of object can reach 100 million Tesla and beyond. Okay, so they are absolutely immense magnetic fields. And there is some really important questions about how do charged particles and plasmas, more on that in a minute, behave in the presence of these really very strong fields. So I'm now going to that's a sort of brief intro. I'm now going to just give you some sort of signposts about where we're going in the talk, just so that you can keep track of where we are. So I'm going to talk a little bit more about those sort of extreme conditions. Then I'm going to talk about how we're trying to make those extreme conditions in the lab, what sort of things we can get. Then the meat of the talk, if you like, is the tools that we're developing to actually measure these extreme conditions, and then I'm going to give you a sort of an update on some of the key experiments that we've been doing and we're trying to do. So part one. So I mentioned these red dwarfs. So what's interesting about these, gas giant planets, red dwarfs, the surface of white dwarfs, is you have this really weird state of matter. It's weird because it's not cold like this solid state table where we know how to describe things, and it's not so hot that everything's a plasma and it's well described by plasma physics. Instead, it's in between. It's this warm, dense, we call it warm, dense matter. And that's where we really don't know how things behave. So it happens at around about cool temperatures of only 10,000 Kelvin and densities of around about 1 gram per cc. There's a range. And that corresponds to pressures of around about 1 bar to 100 megabars, if you get the temperatures right. And so in this sort of green area is where we don't really understand exactly how to behave matter. And so it's kind of cool to try and do experiments with those. And so there's a key research question that we're trying to answer. I'll give you a spoiler, we haven't answered it yet, which is exactly how does heat flow inside these complex plasmas. So in a plasma, where I'm going to talk more about those in a minute, but where you have electrons and ions, heat can move really quickly between the electrons and the ions because there's only collisions. And you're just colliding an electron off an ion and it moves some energy across, and it happens very quickly. In warm, dense matter, the ions are still kind of connected to each other. They still talk to each other. They're coupled. I've drawn them as springs here. And so when the electron hits it, it kind of makes everything move around a little bit. And so heat transfers much more slowly. And so we don't really know how that happens, and that's something we really want to measure. So the next part, as I mentioned, there are kind of two sides to the bits of research I'm doing. So back to the field side. So how strong is a strong field? So in those of you who are at university, you'll be learning electromagnetism. There's a field called quantum electrodynamics, QED, which is the study of charged particles, magnetic fields, and electric fields, where you include both quantum effects and, so that's like the weirdness of quantum mechanics, and relativistic effects, which is things moving really, really fast, close to the speed of light. And the key bit of the physics from that is that in QED, we think of there's no such thing as a vacuum anymore. Well, there is, but the vacuum is this sea of virtual particles that appear and disappear. I've made this funny little movie up there. And they just appear and disappear all the time. And they're not real, they're virtual. So what a strong field is if I put a really, really strong electric field into the vacuum, then it can pull those virtual particles apart, and they never get to come back to each other and combine. And so it turns a virtual particle into a pair of real particles. And that's the field that when that starts to happen is something called the Schwinger field, after a famous physicist from years ago. And it's really high. So just to give you an example, in terms of electric fields, it's about 10 to the 18 volts per meter. I'll cover that in a minute. And in terms of magnetic fields, it's about 1 billion Tesla. That's the easy one to remember. And so one of the key questions we're trying to ask at the moment is how do charged particles respond to these very strong electromagnetic fields, in particular a process that's called radiation reaction. So whenever light interacts with a charged particle, it makes it move around, and that makes the particle give off more light, and so there must be some energy balance, and so the charged particle must lose a bit of energy. So, and when there's lots of particles around, i.e. photons around, i.e. it's a really, really strong field, we don't really know how to behave, to describe it, okay? It's called strong field radiation reaction, which is something we're trying to look at. So in sort of a weak field, so we can think of single photons, it's literally just a photon bouncing off an electron, and there's the electron reacting. In strong fields, it's lots of photons hitting it at once and only one coming off, and it's quite complicated. And like I say, we don't really know how it's going. So what we're aiming to do is try and study these sort of extreme conditions in the lab. So to do that, we need to create the extreme conditions, and we need to probe or measure the extreme conditions as well. And so hopefully I'm going to convince you that actually laser-produced plasmas and high-intensity laser experiments can do both. So that brings me on to part 2. So how do we go about making these extreme conditions in the lab? So it's quite a diverse audience. It's really nice to see such a wide range of people, right from my family down here to my mum, including my kids and my mum and dad and wife, but also other students and other people visiting the department. It's really nice to see. So I've gone right back to basics here so that everybody knows where I'm going. So what is a plasma? So there are 3 states of matter. Yeah? So you've got solids, yeah? You've got liquids, some water here, and you've got gas, which you're breathing, the air you're breathing at the moment. Okay, so solid, the particles are really close together, they're bound together. Liquid, they're free to move around, but they're still very closely bound to each other. In a gas, they're free to move around. So and the way you get from a solid to a liquid to a gas is you just put more and more energy in. So you heat up a solid, it melts to a liquid. You heat up a liquid, it boils and becomes a gas. If you put a lot of energy in, then you can actually get to the point where you get to plasma. So why is that happening? So here are 2 particles, 2 atoms in a gas, and if they collide together, if they collide with enough energy, then some of the electrons can come off, and I'm left with free electrons and charged ions, and then and if I have enough of those in the system, then that's a plasma, and it starts to behave very differently. So I'll say there aren't 3 states of matter. I'm going to say there are 4. I've added one on the end, so there's the 4th state of matter. So how can we make plasmas? Okay, so that's the next thing. So this is where the safety notices come in. So this is the first one, which is the one I'm going to turn the lights off for, which hopefully I can do. Okay. So the first thing is, so I mentioned putting kind of energy into the system and making them collide. Actually, that's really hard. So to just heat up a plasma, if I took a block of aluminium and tried to heat it up so that it was a plasma, I'd need to raise the temperature to sort of more than 11,000 degrees, which is really, really, really high. So there's another way, which is you can actually pull the electrons off the thing with an electrical current, or not electrical current, electrical field. And so that's what I'm going to do here. So the safety notice is, do not approach this whilst it's on and touch it. It will only run for a very short period of time, but you mustn't touch it. That's it. Only I'm allowed to watch it, and I have a special key to do that. So I think Ollie's got one as well, in case it doesn't work. So hopefully this is going to work. So. And the other important thing is I've got to remember, after I've turned it off, to discharge it. So if I forget to do it, shout. Okay. So what's going to happen is we've got a box here which is generating about 10 to 15,000 volts. You take the key out. And that's going to be across these two wires, which are just standing there. It's going to form a plasma, and then heat is going to make the plasma come up. So hopefully it's going to work. It's all an act, don't we? Okay, so there you go. There's a plasma. I'm not allowed to leave it on for too long or it gets too hot. So, when we were building the test one, the first ones were made out of aluminium, and they just snapped. So I'll do it one more time. So there you go. There's a real plasma. Don't get to show those in real lectures very often. So that's one way we can make a plasma. Let me remember to put the... Thank you. I knew I'd forget. It's off. Yeah, okay, that's done. So. You are, that's true. So there's another way we can make a plasma, and that's with a laser, which is, hopefully you got that because that's what I do. And so I've got another demo. This one isn't as dangerous, okay? So it's much more, we've had this for a while. It's all safely enclosed. If you were to break in, shine the laser in your eye, you'd get blinded, but hopefully nobody's going to do that. There might be a small pop, okay? That's the other thing. So in our experiments, let me turn on the laser. We take a laser pulse, a really intense laser pulse, and we focus it down to a really small spot. And that makes it bright, powerful enough to actually ionize matter. Effectively, it's the electric field of the laser is pulling electrons off the atoms again. So it's very simple. So we've got a much safer version here. So instead of the lasers that we use, which are millions of billions of watts, this is a few milliwatts, okay? So it's not, but we're going to focus it down, and if I spray this in, you can see where we're focusing the laser. You can see at that point there, if I put this balloon, it's going to be intense enough, hopefully, to show you that we can pop the balloon. If it's not at the focus, it won't be. So hopefully I've not sprayed too much gas in there that it won't work. So I'm only going to do this once. So. Well, I might do it twice. Okay, so when it's down here, it's not at focus. It's not ready to pop it. If I carefully align it, oh, there's too much gas in there. I think I pressed go too much. I'm going to leave it a second to settle, and then I'm going to come back. That's disappointing. So, I tell you what, I will come back to it, because that's fine. I want to show you it. I'll have another go. But I know I've got at least 2 people in the audience who can vouch that it does work, because they've seen it before. So I'll come back to that. Let's move. I'll put my thing down. Oh, it's disappointing. This was the one I was worried about, not that one. So the next thing I was going to talk about is a little bit of maths, okay? So what's not gone on here, actually I could kind of change it, is we're taking the energy that's in this laser pulse and focusing it down to a small spot. And so why does that get us to the conditions that we need to make a plasma? Well, that's because we're creating a more intense beam of light, okay? So the intensity, this is the math, don't we, is just the amount of power we have in the laser, and it's divided by the area. So we measure it in watts per square meters. And that power is just energy divided by time, the energy delivered per unit time. And so the units of it are watts per square meter, okay? And so what we're doing is we're taking a beam, focusing it down to a really small spot, and then it's not working. And that's just as like if you've ever tried to focus sunlight. So just to give you an idea, sunlight on Earth, on a sunny day is around about 1,400 watts per square meter. So quite a lot. If you got a 10 centimeter lens, so this one is 2.5 centimeters, so a bit bigger lens, and each second it's collecting 10 joules of energy. So that's about the energy of one of the laser pulses we're using in experiments. And if you focus that down to a small spot, then you get a huge intensity, about 100 billion watts per square meter. Okay, just with sunlight. If you do it with an intense with one of the lasers we use, we have 10 joules in our laser pulse. It exists for a very, very short amount of time. It's just for 40 femtoseconds. Now, just to give you that, so a femtosecond is 0.001 seconds. Yeah? Okay, I'm not going to say them all. So it's 1/4,000,000th of a second. It's tiny. So if I then take one of those lasers and focus it to 10 microns, it's 10 to the 24, or a trillion watts per square meter. And that's the sort of intensities that we get in our experiments. And so if you've ever taken a magnifying glass and used it to burn things on a sunny day, that's getting to pretty extreme temperatures and densities, not compared to this, okay? That's the point. So what kind of conditions can we actually create in our experiments? So one of the key things is that we do these experiments incredibly quickly. So the lasers are only tens of femtoseconds or tens of picoseconds long, and so nothing has time to expand. Okay, so if you hit a solid target and you hit it with a laser pulse, then it rapidly, depending on the heating mechanism, it rapidly gets to really high temperatures. It doesn't expand, so you have really high densities as well. So in the experiments we're trying to do, there are two methods we use. One is we directly heat it with a laser. So that's only very good at heating a really, really thin target. So just 100 nanometers, much thinner than a hair. And that one we can get to like 10 million bar, 1 million degrees, and that all happens in 40 femtoseconds, the duration of the laser pulse. There's another method that we're quite keen on, which is where you have an intermediate step. We go from a laser to a plasma. That plasma is really hot and it gives off X-rays, and we use those X-rays to heat something else. That all happens in around about 40 picoseconds, but it can heat a much thicker target, which is quite useful. So that's the sort of temperatures and pressures we can produce. I think it's still a bit foamy in there, so I'll keep coming back to that one. So as I said, two sides. The other one is the strong fields. So some of the strongest electric fields on Earth are at the focus of one of these lasers. The electric field is related to the intensity. It's just like it's the square root of the intensity if you like maths. Okay. So do you remember I said that the Schwinger field, this strong field, happens at around about 10 to the 18. So that's 1 followed by 18 zeros volts per meter. If that experiment with the sun that I just talked about, if I focus that down, I get to about 10 to the 7 volts per meter. At the focus of one of our lasers, it's about that much more powerful system. It's about 10 to the 14 volts per meter. Okay, so if I compare the critical energy to the electric field to the critical electric field of the Schwinger field, it's tiny. It's nowhere near. It's like 10,000 times lower. Okay, so that means that so if I have a single electron, there's my laser pulse. The electron's just sitting there, and I interact it with the laser field. I'm not going to see anything close to this strong field phenomena. But we're lucky. There's a trick. So when we collide a particle that's moving close to the speed of light with the laser pulse, then it sees a much stronger electric field. Okay, so what we're going to do is we're going to pass them through each other. They're both moving at the speed of light. Those of you who are doing physics here, you'll soon be doing relativity if you're in the first year. If you're older than that, you've already done it. So in relativity, when we transform into the frame that's sitting with that electron, the electron now sees a much higher frequency and a much stronger laser field. And so if we have electrons that are going at very, very close to the speed of light, so this close to the speed of light, which if you've done relativity corresponds to a Lorentz factor of about 1,000, then actually what's important is that Lorentz factor times the electric field. And in our experiments, we're getting up to about 1/10 of this Schwinger field. And that's close enough for the physics that we don't really understand to start to kick in. So if we can do that experiment, it will work. And so that's that, don't we? Yeah. Okay, so part 3. How on earth are we going to... Shall I give it one more go? Yeah, I'll give it a go. It does look like it's calmed down. I don't think it's going to work, but just to show you that it works. Or do they say never go back? Fingers crossed. No, it's just not going to go. I think there's too much dust on the lens. It's kind of picked up. So. The thing is, the whole thing has to be kind of finely balanced so that it's safe enough to do. If we turned up the laser power by a factor of 5, it'd work every time. But I will have a go afterwards with the lens cloth and see if we can fix it. Okay, I won't come back to it. So what sort of tools can we do to measure the extreme conditions? So one of the problems is that in all the experiments, we can only create these conditions for a really, really short time. So I mentioned that our high density temperature experiments only exist for sort of around about 10 picoseconds. So that's that many seconds. I lose track. Yeah, it's just such a small number. Yeah. Worse, the strong field, when we're trying to do that, that's only the fields of the focus. They only exist for 40 femtoseconds, so that's 4 with all these zeros. They're not there at all. So if we want to do any experiment to sort of see these, we need a really fast camera. Okay. What do I mean by that? If something's moving really quickly, you need a fast shutter to image it. If once you get to the point where you can't move the shutter quickly enough, then you leave the camera open and you shine the light really quickly. So this beautiful image from the web of a cup of tea being spilt, travesty, it needed a light flash that was about 150 microseconds. To do the experiments that we do, we want a flash that is measured is less than a picosecond. So for those experiments where we're trying to look at warm dense matter, we can only create this warm dense matter for around about 10 picoseconds, and that's because it rapidly expands and cools. What we're trying to look at is how quickly the heat moves around in the system. So we need to watch it throughout that thing and actually take snapshots. And one of the nice ways to do it, the other thing is we need X-rays. Okay, so this material is, although it's very thin, it's very, very dense. So actually, if we want to sort of see inside it, then we need X-rays to actually penetrate it. Just like you need X-rays to see the bones in your body because they're really quite dense, you need X-rays to go through these dense plasmas. A nice way, it's not the only way, but a nice way of working out what's going on is to do something called absorption spectroscopy, or X-ray absorption spectroscopy. And so this isn't X-rays, this is an example of optical absorption spectroscopy. So this is the spectrum of the sun, measured on a fairly nice absorption spectroscopy machine. And when you get the sunlight, you disperse it, and you get the colors of the rainbow. But if you look at the details, you can see little lines where sunlight's been absorbed. And one of them, this D line here, is from helium. That's actually how helium was discovered. It's why helium's called helium, because helium is helios for the sun. And so that line tells you that there must have been some helium in the atmosphere of the sun to be getting absorbed. And so we're going to do things a bit like that with the X-rays that we generate. Again, the other half, for the strong field. So what I'm showing you here is a little movie of a laser pulse that comes in and focuses. Remember, like this failed demonstration? Remember that? I'm going to remember that for the rest of my life, don't worry. It's going to focus down, but because it's a pulse, it's only really, really strong for a very, very short period of time. So if I have a long, big electron beam for this colliding pulse, there's my electron beam, only a very small part of the electron beam interacts with the really, really high field thing. So what you want to do this experiment is you want your electron beam to be really closely matched to the size of the laser focus, okay? And so, hopefully, is that going to work? Okay, so here's my smaller electron beam, and if I time it right, oh no, I didn't time it right, okay? Let's try again one more time. Yeah, there you go. Okay, hit it that time. If you knew it was that easy, hey, Jason? Okay, so the tool that we're going to use to do both of these is something called a laser plasma accelerator, or a laser wake field accelerator, which I've been working on for a couple of years now. Okay, so this is a nice picture, or an actual picture of one of our accelerators. I think it was on the experiment Brendan was running. I don't know who actually took the picture, but I mean it's just a camera on the lab. So okay, and so what you're looking at here is our plasma. This is about 2 centimeters long, and then out of the end of this comes our electron beam. And I'll tell you more about that in a minute. So this all started with this paper back in 1979, okay, so by Tajima and Dawson, where they predicted that if you had plasma densities of around about these sort of plasma densities, and you'd get giga-electron volts of energy in a centimeter. So 1979 was a very good year for laser wave accelerators. It's also when I was born. So how does it work? So there's this paper a couple of years ago that I really like about how ducks, little baby ducks, why they follow. Have you ever noticed baby ducks on a pond? They're evenly spaced behind the mummy or daddy duck. Okay? Yeah, so why is that? It's in this paper. It's because they surf, the mummy or daddy drives a wave, and then the little ducks surf the wave behind them, so they don't have to swim quite as hard. And so if they're exactly nicely spaced, then they save a little bit of energy. And that's what we're doing. So this is the laser, and these are the electrons that we're trying to accelerate in the wave. So here's my laser. It's going in that direction. It's going through a plasma. When you have a laser going through a plasma, it's so strong that it actually, the light pressure of the laser pushes the plasma out of the way. Except it only really pushes the electrons because the ions are much, much heavier. And so if you imagine that I'm the laser and the plasma's streaming towards me, because I'm kind of, I'm not going to run at the speed of light. We're going to switch to the laser coming that way. And so the electron, when the electrons get towards me, I'm sort of pushing them out like that. And but the ions are going to stream through me and then they're going to get pulled back in behind me so the electrons are going to get pulled back to where the ions are, okay? And they're going to overshoot and form a wave. So there's some electrons, they're streaming towards the laser, and they do something like that. And that's a picture from a simulation of what these plasma waves look like. And that's the process that's generating them. What's really lucky is that if we do this just right, actually some of these electrons, they don't overshoot. They're constantly being pulled into this first bubble of plasma, and they actually start moving at the same speed, or very close to the same speed as the laser pulse. Actually, they go faster eventually, because the laser's inside a plasma, so it goes a bit slower than the speed of light. And so that means that we actually sweep up some electrons from the plasma, and they get injected, and then out they come. Which is really good, because I was very lucky to be involved when I was doing my PhD, working with Zulfikar, I've lost her there, yeah, and others, that we found, it's almost exactly 20 years ago we were doing the experiment, that if you do this right, you get quite nice electron beams coming out. So there were 3 groups that did it around about the same time, we were first, but I'm going to talk about this picture from the French group, sorry Zolf, because I like it, because what they showed is up until that point, most of the electron beams looked like this. They were a bit of a, okay, so they were there. We knew that we were driving these waves. We knew they had the fields that could accelerate particles, but you couldn't get nice quality beams. And if you do it right, boom, you get a nice narrow energy spread beam coming out. Back then, these were with only 10 terawatts of laser pulse. So and the plasmas were only a couple of millimeters long. Since then, there's been fairly steady progress. So this is a little database we have of all the different laser wakefield experiments that are going on. It's not very up to date, which is why there's no experiments down over here. But you can see I've kind of highlighted the record at each point, and you can see that it kind of goes up roughly every 2 to 3 years. It doubles roughly every 2 years. Why is that? Well, I won't go into the details, but it's basically just because we're using more and more powerful lasers. So this is laser power against the electron beam energy, and the higher power the laser you have, the more energetic electrons you get. And so that if you have a petawatt laser, a couple of groups are now getting sort of 8, 10 GeV electrons out of these things. Keep pressing the wrong button. So what sort of electron beams can we get? Well, bear in mind the experiments we're trying to do with them, they have high energies. They have these giga-electron volt energies. So that's a gamma of around about 1,000, 2,000 for the strong field stuff. They have a micrometer size. They're very small because they come out of this tiny plasma. And they have a very short duration. And that's exactly what we need for those strong field physics experiments. So can we collide these electron beams with another laser pulse to study these strong fields? So they're not perfect. Actually, for the experiments that we're doing, these are sort of typical electron beams that we get in black. Okay, I won't go into the details of what the other curves are. Need to stop pressing that. So flipping back to the sort of the warm dense matter type stuff we're trying to do, these laser wake field accelerators aren't only sources of electrons, they're also sources of the X-rays that we need, or we want to do the X-ray absorption spectroscopy with. And so that's because the electrons, as they come in, once they're injected into this bubble, they overshoot and they wiggle around. And whenever you make electrons wiggle, they make light. The properties of the wiggle and the electrons mean that these are very, very bright, short flashes of X-rays that come out of the laser wake field accelerator. And so these are, these started to be seen in the early 2000s. Since then, we've been working on making them significantly brighter. And so this is around about where we were. I think this was an experiment we did in Sweden in 2009. This was Michigan in 2010. And this is when we started using the Astra Gemini laser. And now you can see not only have we increased the energy of the X-rays by a factor of 100, or a factor of 10 or so, the energy has increased. The brightness, how many X-rays you have at per energy bin, has increased by 10,000-fold. And so now we're right at the point where we're saying, have we actually got these X-rays, which are really short flashes of X-rays, bright enough to do this X-ray, femtosecond X-ray absorption spectroscopy? So, final part. Can we actually do some experiments to probe these extreme conditions in the lab? So, most of the experiments we do are at the Gemini laser, which is, it's called Gemini because there are two beams. It's at the Rutherford lab in Abingdon. I think Zulf was there today. So, and it has two beams, each with 10 joules and 40 femtoseconds. And so the idea is we use one beam to drive the laser wake field accelerator and another to create these extreme conditions. And because they're basically from the same laser system, it's moderately easy, it's definitely doable to overlap them with micron precision and femtosecond timing, so we can do these experiments. So I found a picture of me actually in the lab, which was a few years ago. So. Okay, so let's go back. Do you remember the key questions we were trying to answer? So one is, how quickly does heat flow in dense matter? So that was, I'm not going to go over the slide again, but that's the question. So we need to find out whether we can do the X-rays first, the absorption spectroscopy first. And so I've got a little sort of history, potted history of some of the work towards that. So it's all a bit more recent. So it's sort of, the last 10 years or so, less than 10 years. This was some work done in Canada where this was a very noisy spectrum. It was the first one, so fair credit to them. But even this spectrum, that they needed to sit and turn the laser on 150 times to get enough photons to make a measurement. This is one that we were involved in America, where again, to get a spectrum, you needed 330 laser shots to get us this spectrum. This one's actually starting to show what we're looking at because you can see a difference between hot and cold. More on that in a minute. Another one. We did in Sweden with another group as well, which is needed 100 shots per laser. And then this is a very nice result from the French group, which was still needing 50 shots per spectrum. This is a real problem, because every time we fire, we're trying to watch something evolve, so we need to kind of vary the time between when we hit the plasma and when we take the picture, or when we take the X-ray image. So you need to take lots of shots to build up the time series. And actually, if you have a big laser which can produce the really extreme conditions, they don't fire very often. So the Gemini laser that we use fires, or when we're doing a target, it fires about once every minute. So waiting 300 minutes to do one data point before you do another one is a little bit tedious. Okay? And also a waste of time. So it's really important to try and get this X-ray source bright enough to try and do this in a single shot. And so I mentioned that sort of progress in the brightness, and the good news is it works. So this is a paper that Brendan did a couple of years ago, and so it's still very noisy. So we're now able to see in a single shot, that's some of these features that tell us what's going on in the plasma. I'm going to explain those in a minute, don't worry. This one's unpublished, but actually we've now got even better, and so now you can see there's a lot less noise, and the blue is comparing it to a long pulse data from a synchrotron, showing that we're actually getting the same results. And so now, if you were paying attention, you'll notice we can see further away as well, which is important. More on that in a minute. Why is that important? Because what's going on here is when the X-rays get absorbed in the plasma, or in the warm dense matter, this is a cold target, it's not warm dense matter yet, so the stuff that's going near this edge, it's called near-edge spectroscopy, or X-ray absorption near-edge spectroscopy. That tells you everything that's going on with the electrons in the system. So it tells you, essentially it tells you the electron temperature. What's going on over here tells you about where the ions are in the system. So if you're in this warm dense matter state, how strong these modulations are and where they are tell you how correlated the ions are in the warm dense matter. And so this is called EXAFS over here. And so we can now do that in a single shot. So the idea, which you can see Rory's paper from a couple of years ago as well, is to use experiments where we create the warm dense matter and combine it with the probe that we have, which is now, after years of work, bright enough, and then you can actually see differences in the electrons and the ion temperature at the same time. And different models predict different rates, and so that's what we're trying to do. And unfortunately, we tried to delay this talk for long enough, but the experiment where we're going to do it next is happening in May, so it's a bit early to tell you whether there are it's too early to tell you whether there are new results on that one. So it's coming. Watch this space on that one. So the second question, how do charged particles respond to very strong electromagnetic fields, this thing called radiation reaction? Oh, I didn't want to go through the video on that one. Anyway, so this is the sort of experiment, nice picture from Jason. So we take our laser beam, we focus it into our gas jet that you saw a picture of, and then we have another laser beam that focuses on the electron beam, and we measure the electron beam energy. It's going to lose energy, so we want to see how much energy it loses, and we measure the flash of gamma rays that come off as well. The problem is, it's really hard to hit the thing. Okay? So now I'm looking at the two beams coming from either side, but they're hitting a target. The red is the laser beam, and the blue is the electron beam, and this is roughly the sort of level of stability we can get. If you're watching, it goes green when they hit. Okay? So this is tricky, okay? Because so we don't get a collision every shot, so it's not possible. Okay, not yet. Maybe in the future, but certainly with the existing lasers, it's not possible. The other problem is that the electron beam isn't the same on every shot. So if we're trying to look for changes in the electron beam to do with when it had a collision, we might misinterpret one from the other. So the only way to do these experiments, we realized, was to actually work out which ones were the collisions before we did the analysis of what was happening to the electron beams. And so that's what we did. So you do that just by looking at what the electron beam does without the second beam. And then when you take your shots, you find, oh, look, these ones over here are really bright. We've hit the beam. Great, we've identified those. On this experiment done in 2018, we only had a grand total of 4 successful collisions, okay? But it's enough, because if I look at the energy, electron beam energy on all of those 4 shots, they're all down here, okay? So they're all below 500 MeV. Whereas if I look at the electron beam energy on a shot where there's no beam, where there's no colliding beam, then there's a broad spread, but the average is above 500, and so the chance of seeing 4 shots which are below 500 MeV or by random chance is quite low. Okay, it's about 1 in 4. Okay, so seeing 1 is about 1 in 4. Seeing all 4 is about 1 in 350. So it's getting to look like we've seen, the electron beam's lost some energy, but we're not quite there yet. Okay, so the other thing is, I told you we look at those gamma rays. We also measure the energy of those gamma rays. So if we're seeing radiation reaction, the more energy the electron beam loses, the higher energy the photons that they produce. And so if we're looking at the energy of the electron beam after the collision, that's the final energy, that means the lower the electron beam energy, the higher the photon energy. Pretty much every other radiation generation process goes the other way. So the chance of seeing our 4 data points with this correlation in this direction actually goes to less than 1 in 3,000, which is at a point where you start to say, as a physicist, we think we've seen evidence for something happening. So this was the first time we managed to get experimental evidence of this radiation reaction. Of course, it's actually about doing physics, so what we want to know is, did we see a difference between these the models that people predict? And so the first, the curves aren't appearing. Oh no, I don't know, that's a disaster. Never mind. I didn't spot that in the end. Okay, I'm going to have to draw them. You're going to have to use your imagination. Okay? As I say, so if we didn't have any radiation reaction, we expect a green blob over here. Okay? And anybody who's interested, I can show you them later. If we use a sort of classical physics model of this radiation reaction, then it's kind of here. It's kind of close to the beam, but it kind of starts to disagree over here. And if we use the strong field QED model, it actually overlaps all of them. So we're starting to see agreement with strong field QED. It's not enough to kind of really tell the difference. To do that, we need more data, lower experimental uncertainties, and plots that work. So we have now done a follow-up experiment, and I don't know if Ava came down. I didn't see her come in. So one of my PhD students is just finishing, is busy analysing the data on this, and well, watch this space. It's very interesting. It's too early to say. So that comes to the end of my talk. Hopefully, I've convinced you that lasers can create and probe. Lasers and plasmas can create and probe these extreme temperatures and densities. We're making real progress in 2 key areas. We now have this bright enough X-ray source to probe warm dense matter on a femtosecond timescale. And we've already seen evidence for this strong field QED reaction, but there's still work to be done, which is good because I'm not ready to retire. And I've kind of told you where we're up to on those. So before I finish, I just wanted to talk about the team. So this is the team that I've been working with very closely over the last five or so years. That was when I was funded through the ERC. In particular, I'd like to highlight Jason, who did a lot of the work on the radiation reaction stuff, he's over there, and Brendan, who's leading the work on the X-ray absorption spectroscopy, but everybody else is there as well. I won't mention everybody's names. I've also been working with loads of other people over the years as well, so I'm sure I've forgotten lots of people, but these are all the collaborators and actually good friends that I've built up over the years doing this as well. So, and then finally, it is International Women's Day today, and so I just wanted to highlight, I've been very lucky to work with a lot of very talented women, which I've just highlighted from there as well. So, I'm not going to go through the list of names, but thank you very much, everyone. So, I'm very happy to answer any questions, and I'll put the credits in.
Well done.
Thank you.
I think before we open up for questions, shall we give Stuart one final chance to get the experiment to work? Do you think? Yeah. Third time lucky?
Any suggestions how to clean it from here? Blood removal. I mean, it's like a real laser experiment, so. It's not going to. I can see that when there's this much dust on it, it doesn't work. A bit more. It was the laser, honest.
We all believe you. It really was the laser.
It was the laser.
Thank you very much, Stuart. So we're going to share questions from in-person and online. Annabelle, I think you have some questions. Have you?
There's some, I think, coming out. I've just put a comment in that it's a bit behind. There's a bit of a lag.
Okay, so shall we start in the room? Yes. And could you wait until the mic gets to you so people online can hear? Thank you.
Yeah, thank you so much for the talk, Professor Mangles. I wanted to ask a somewhat advanced question about when you're accelerating the electron and it sees a different electric field,
Yeah.
it would also see a magnetic field that's, I wanted to ask you, is that something that you have to take into account?
It is, absolutely. That's a really good question. I've kind of skipped over that. So actually, you might think, it sounds like you have a bit of a physics background. So what's really important is there's the Lorentz invariant associated with the electric field of the laser, which is to do with E squared minus B squared. And so you have to make sure it does both. So actually, for example, if you just want to make, I talked about these pairs becoming real, you can't do that with a single laser pulse because the B disappears. You need 2 laser pulses. But you do still get enough for the strong field stuff to kick in. But does that sort of answer your question?
Do you do anything in the experiment to mitigate the magnetic field?
No, it's needed, if you like.
Okay, thank you.
Okay, shall we go online?
Yeah, I think the question online was quite similar, but I think asking for your general comments on whether you can specifically generate high magnetic fields using lasers.
Okay. So, they are high. So they are already. They are. What did I say? So the ratio is the same. So they'll be about a 10,000th of the critical magnetic field as well. So, quick answer.
The gentleman with the yellow jacket. Thank you.
Hello, thank you. When the photon pulse, the laser pulse, is so short, do you not get to the stage whereby it's sort of less than 1 wavelength?
That's a really good question. You can. It's quite a bit shorter. So for the laser wavelength that we're using, which is around about 800 nanometers, so sort of just a bit redder than the reddest light in the room. You can't quite see it. The wavelength corresponds to, 1 cycle corresponds to about 3 femtoseconds. So with our laser pulses, which are 40 femtoseconds, it's still many cycles, so it's okay. But there are labs here in the basement which are getting down to sort of 3-4 femtoseconds, where, I don't know what the current record is, where actually it really is, you do start to need to think about, is it many cycles or not? So
and therefore, do you get a very wide bandwidth?
Absolutely, yeah. So even in ours, I say it's 800 nanometers, the bandwidth of our laser pulse is still 40 nanometers or something like that. So there's always this interplay between how short your laser pulse is and how wide the spectrum that comes in it.
Can I ask one more question? How do you focus a laser? Because the lasers that I've used are already pretty well focused.
That's a good question. So as it's not going to work, I can do this a bit more. The first thing you do is you expand it. So if you see the laser up here, I don't know if it'll work actually, it comes out this tiny little laser beam. There's a little microscope lens here, which focuses it down, and then it expands again afterwards. And then this lens actually lets us get to a focus as well. So the way you focus it down is rather bizarrely, you make it bigger first, and then you focus it down even smaller.
Okay, another one online?
So someone wants to know how the warm dense matter relates to the environments near black holes, so in particular for supermassive black holes and active galactic nuclei.
Okay. So if I'm honest, I would say that the warm dense matter is more relevant to sort of fairly cool stars, like red dwarfs, and the surface of things like white dwarfs, and the interior structure of gas giant planets. The stuff that's relevant to black holes is much more these really strong magnetic fields or electromagnetic fields, because the plasma that's whizzing around and being swirled around a black hole generates fields which get amplified, and then that's when you get these really, really strong fields. So I don't think there's any warm dense matter very close to a black hole. Somebody can correct me if I'm wrong later. So only if they get me a drink.
Right in the front row.
How the energy density that you achieve compares to laser confinement experiments in fusion reactions?
That's a good question. So if you remember, one of the things I said was the experiments that we're doing with these short pulse lasers, we hit it and then we probe it before it's had time to expand. So we get the high densities just by basically, they stay the same density as solid matter. Another way to do really high energy density physics is to get matter and squish it first. So you can get quite a bit higher energy densities in compressions. But don't forget the lasers that we're using are around about 10 joules. So if you want to do a compression experiment, you need about 1 million joules to do that. So yes, you definitely get more extreme conditions in those, but it's still actually getting to a similar state, and it lets you study some of those things.
One more online?
This is maybe a bit more of a technical question, which is how is the pointing instability dealt with to make the electron and the laser collide with such high precision?
Well, I don't think it is. So, as I was trying to show, that actually most times we don't hit it. So the most recent experiment, we took a lot more shots and we've hit it hundreds of times. So there's a lot more data coming through. But we are still basically just hoping and hitting. You know, we get it as close as we can, and then we just wait until we get a collision. So it's quite an effective way of doing it, actually.
So there's one just over there, but I'm quite disappointed in this side of the room. Okay. Thank you.
Yes, I would like to ask about what are your hopes to achieve within the next couple of years in this field?
So, I mean, that's next couple of years is really quite easy to answer. So if you'd asked me 10 years, I might struggle. That would sound like an interview. So we've got an experiment coming up where we're going to do this pump probe warm dense matter stuff. So I hope in the next couple of years we will really be able to actually answer some questions about how quickly does heat move around inside warm dense matter, and it's quite important because how heat moves around in a material actually tells you about something called its equation of state. So how it actually the pressure and temperature vary inside a planet, which will tell us stuff about how gas giant planets are formed and things like that. And again, for the strong field stuff, imminently, I hope, we'll be able to tell you whether or not we've really seen a difference between the different models. And then the next thing will be actually trying to get it precise enough to sort of really interrogate the details of those models. And then there's one other one, which is what I didn't say, is if you get it even stronger, you won't just get photons coming out, you'll actually get real electron-positron pairs coming out as well, and we'd like to see that too. So that's something else that we try. You need a bit more. You need a slightly higher electron energy beam to do that, I think. So, I said we were at like 0.1. You probably need like 0.5 to get to that, so we're not quite there yet on Gemini. But they're building us some bigger lasers, which is good.
All right, thank you. I also want to greet you from your old colleagues from Lund, Christopher and Michael, I think. I would like to say hello.
Nice to hear from them, yeah. So, thank you.
Okay, so we'll have two more questions. No, one more question then. So, thank you.
Hopefully I can ask two really short ones.
Okay.
The first one is, when you're talking about high density matter in this case, are you talking about high density for a gas? As in, because it sounds like you're saying it'll have the same density as a solid we would have in a room.
So what we really care about, actually this gentleman over here mentioned the word, what we really care about is energy density. So that it's the fact that it's dense, it's about the same density as this, but really, really hot still. So normally when you heat something up, it gets really hot. It expands. So if you can have it solid density and really, really hot, then you're still in this warm, dense matter state. You can get there by making it really, really dense. And actually the compression experiments get really interesting as well. If you can do that, then you get weird quantum stuff happening in the warm, dense matter. So we'd like to do that eventually as well. So.
Thank you very much. The other one is when you're saying you sort of concentrate this or focus this laser and it produces really high strength fields. Is that like having lots of photons overlapping and a sort of electric field from each of them add in a sort of vector sum to produce the high field? Is that how it's being produced?
Yeah, I think that's a pretty good description, yeah. So yeah, you could think of this laser beam that's being focused as lots of little laser beams that then combine at the focus.
So it's critical that it's coherent?
Yes.
Yeah, okay.
No, because it's not coherent when you do it from the sunlight. So it's not completely critical. So
a conversation for
afterwards. Yeah.
Thank you very much.
Yeah.
I think there's one final question online.
Yeah, so there's a question which is how do you extract the electrons that are trapped within the plasma that cause this?
Okay, sorry I didn't make that clear. That's a great question. So the great thing is they're going, so the question was how do you trap the how do you get the electrons out of the plasma? They just come out, it's great. Basically, we just fire the laser into the plasma and out, if you do it right, out come a beam of electrons and a beam of X-rays that you can do these experiments with. We don't really have to do anything. So.
Okay.
I mean, yeah.
Well,
sorry.
A few things maybe.
Yeah.
Okay, so thank you very much, Stuart. I'd like to hand over now to Zulfikar Nadmuddin. Sorry, Zulf. That was a dreadful pronunciation of your name.
Zulfikar will do.
To give the vote of thanks. Now, Zulf is a long-term and valued advisor and mentor to Stuart. So, please.
Okay. Thank you, Stuart. First of all, that was a great talk, both fun and educating as well. So thank you. I think that was the remit for today. I think the first thing to say about Stuart, and I think Michelle already touched upon it, is Stuart is one of our undergraduates. He's been at Imperial a long time. Maybe not quite as long as me, but he's been here a long time. Since 1997. I've been here much longer. I mean, at the moment, we're very worried about our undergrad students. I know we have lots of conversations, but if you want an example, if you're an undergraduate here, and if you want an example of what our undergrad students come out to be like, I think Stuart is a great example. He obviously knows all of your pains as well, so if you have any worries, problems, you should come talk to him, right? There's going to be 50 at your door tomorrow. You can thank me for that. Stuart tells me while he was an undergraduate, he heard about plasma accelerators. And what he tells me is that immediately he wanted to work in the field, to do a PhD, maybe even form a career in that. And so that seemed to work out very well. Stuart did his PhD with a colleague of mine, Carl Krushelnik, but we worked very closely together. I think he was probably in my office, well, maybe more, I would say, than in Carl's office. Actually, in those days, I did experiments as well, so you may be a little disappointed with the demonstration, but actually, that really was very similar to what our experience was in those early days of, there was a lot of time sitting in the lab, waiting for lasers to do exactly what they were supposed to do, and most of the time it was actually like that. But luckily, he sort of pointed it out during the talk, but he didn't say that much about it. Luckily, during his PhD, there were some really great results. I mean, probably maybe too modest to say it, but there was a paper in Science, there was a paper in Nature. You did mention he was the first author of that. That was the main topic of his PhD work. I mean, that work is actually considered one of the seminal works in our field in plasma accelerators. If anybody talks about a laser wake-field accelerator, it's very common they cite that paper. And so, it's, depending on the metric you use, something approaching 2,000 citations for that paper now. And obviously, that's super successful. As you can imagine, Stuart's thesis swept the board. I mean, won every prize you could think of. So he won, I've written them down because I'll forget otherwise. He won the IOP Cullum Thesis Prize. He won the EPS Plasma Physics Thesis Prize. There's an international prize in the plasma accelerator work, the John Dawson Prize. He won that as well. If there had been an Oscar for best thesis that year, he would have won that too. I don't know if you remember this, but you were my postdoc. So you weren't my PhD student, but you were my postdoc for a few months. Yeah. I don't think you took a single order from me. Not because we fought, but just because there basically wasn't time. He was quickly became a Royal Society URF, University Research Fellow. And the great thing about the URF is that you can sort of make your own career path. Stuart could, I mean, already had straight out of a PhD, had quite a reputation in our field already in plasma accelerators, and he could have just continued to do that work. But I think what you saw from his talk today, he really wanted to follow his own interests, forge his own path, and actually use that URF to be able to do that. 2011, I think you were made a lecturer, is that right? The lectureship was a special one. It wasn't a physics department one. It was a president's lectureship, right? It's president then.
Through that process, yeah.
Which was a very competitive thing. Only 6 awarded through the whole college that year. And so only the top people were going to get that. Stuart got that. As he did point out, he won that ERC grant as well. Those are super competitive. Only a few % of people get one of those, right? Something like that. And allowed him to build his team to do the work that he was talking about. I mean, there have been lots of other achievements along the way. You were made a senior lecturer. I'm asking you because I can't even read my own handwriting. 2015, reader 2017, professor in 2021.
I'll bring you my glasses.
It's too late. I'm almost at the end, thankfully. I mean, all of those achievements, all the time that I've known Stuart, I have to say, probably going back to those PhD days that I mean, not just from our relationship, but I recall most fondly, mainly because, as I said, in those days, I mean, Stuart, there were some other students around at the time, Alec, Louise, Phil, a few others, Chris Murphy when he was around. They would just come into my office, and almost on a daily basis, there would be a new question, there would be a disaster, or some simulation hadn't worked quite right, there would be a paradox which we had to explain. And some of the time I would know the answer to them, quite a lot of the time I would not know the answer to them. I think we learned the subject as we went along. And that's what real research is, right? Where every day we come in to try and learn things. And so that for me is really, I mean, I remember it very fondly because that was the most fruitful time of my career as well. I mean, nowadays, I mean, I said Stuart's managed all these things, but he also has this, he has lots of responsibilities within the department as well. He's head of first year, head of the first year, and he's been doing first year lab as well, and lots of things like that. I'm afraid we don't have as much time to just sit in each other's office and talk physics anymore.
Nice when we do.
Yeah, but maybe that's something we could, well, one day, maybe they'll let us do that. Yeah, okay. Not aimed at anybody in particular. I'm going to congratulate you for your talk again, but I also congratulate you for the work you've done so far. I mean, he's very young to become a professor, so I'm sure there's going to be many achievements ahead that we'll hear about. But well done, Stuart. Congratulations.
Thank you very much, sir. Thank you.
Well done, Stuart. Thank you very much. We are going to reconvene outside in the concourse. There is some wine, I hear, and I'm sure Stuart will be happy to answer more questions over a glass or two of wine.
Absolutely. As long as I've got
So
a glass.
thank you very much for joining us. It worked.